And good evening, AP Physics students. Welcome to your second to the last video of the year here coming up. Talking about double slit diffraction today. So without any more interference, let's get started here. Okay, diffraction. Diffraction is the bending of waves into what the book calls a shadow region. So I got a little picture here, right? If I have a wave coming and the waves go through an opening, the waves bend kind of as they go around the corners. So theoretically, when a waves go through an opening, it shouldn't be able to make it into the shadow regions, as your book calls it, but they do. Because the waves bend as they go through an opening. Okay, so diffraction, the bending of waves as bending of waves as they pass through an opening. Now, in general, diffraction, especially double slit diffraction, talks about wave interference. And remember, before we even start to talk about wave interference, the sources of your waves must be two things. For light, the sources of waves must be monochromatic. And you guys by now know that that means one color, so the light must be all the same color. And it must be coherent. Okay? In other words, if you know, for two waves to interfere with each other, the waves have to have the same wavelength or be monochromatic, same color, same wavelength, and they must start out in phase with each other. I mean, I guess they wouldn't have to, but you know, they at least have to be, you know, in the same plane. So anyway, for waves to interfere, they must be coherent and monochromatic. To get interference patterns anyway from diffraction. Okay, so when do waves constructively interfere if the interference patterns are, if the waves themselves are monochromatic and coherent? They will exhibit constructive interference when the path difference between the two waves is equal to an integer number of wavelengths. So here m is an integer, 0, 1, 2, 3. Waves will exhibit destructive interference when their path difference is a half integer number of wavelengths. Now let me show you a little picture here for what that means. Okay, so let's imagine here I have some monochromatic, one color, coherent light, right? The light starting out in phase. And the light goes from here to here, so the path difference is 0, right? This wave is traveling the same distance as this wave. Well, that means this crest and this crest arrive together, and I get a super wave here, a constructive interference, and I get a really bright spot right there. On the other hand, what if I look up here? Up here, this wave down here is traveling farther than this wave. And if this wave travels an extra half wavelength, that means when the crest of this wave arrives, the trough of that wave will arrive, and the waves will cancel each other out. So when the path difference is half a wavelength, or 3 halves, or 4, or 1.5, or 2.5, you get destructive interference. And with light, a destructive interference is dark. And with light, a constructive interference is bright. So here I have a central bright spot, and then I'll have another bright spot over here. Okay? Now, if we look closely here, if the separation between our slits is D, okay, and this angle here is theta, which means by similar triangles, this angle here is theta. That means for double slit diffraction, our path difference is just d sine theta. Okay? So I'm going to write that out because that's important. With double slit diffraction, you have two sources of light. Each slit is acting like a source. And the path difference is d sine theta, where theta is the angle to your place where the waves are hitting, and d is the separation between the two slits. So, constructive interference, integer number of wavelengths, destructive half integer number of wavelengths. Okay? All right. Well, let's dive into problem 1 here. Problem 1 states that there is a fifth order interference fringe at an angle of 8.8 degrees when there's a double slit diffraction, and the spacing between the slits is 0.016 millimeters. Okay? And then the question asks, what is the wavelength of the light if this is a bright spot at 8.8 degrees? So this is one of the magic equations on your equation sheet under optics. Perhaps one of the last ones, new equations we're going to learn. So here I have the path difference. And if it's a fifth order interference fringe here, what that's saying is that m is equal to 5. All right. So if we plug in what we know here, we would get 1.6 times 10 to the minus 5 meters times sine 8.8 degrees is equal to 5 times lambda. And if I do my algebra there, lambda then would be, let's see here, solving for lambda, I would get 1.6 times 10 to the minus 5th times sine 8.8 degrees divided by 5, and I would get lambda is equal to 490 nanometers, or 4.9 times 10 to the minus 7th meters. All right, so that would put that in the somewhere maybe in the let's see, 400 nanometers would be violet, so this might be blue or indigo. All right, so well, good, nice work, physics students. So as I'm sitting here talking about this video, my dog Raven's kind of watching me, wondering why I'm talking out loud when no one's around. And you might be wondering what goes on inside your dog's mind. And as it turns out, this is a legitimate scientific topic that is being studied right now. Scientists seek to enlist a virtual pack to reveal the secrets, thoughts of dogs, which could help identify better service dogs. So interesting article here about how they're trying to really figure out what's going on inside dogs' brains. So anyway, nice job, AP Physics students. We'll see you tomorrow.